So in the first question on the review sheet for test one, it does tell us that ES is parallel to AT. And it is missing part of the question. Sorry about that. But it's supposed to say which is the correctly set of proportion. So I'm going to put that here. Which is correct. So I'm going to go through one by one so that way we can see. So first, before we can even have proportions, we need to know that the triangles in the diagram are similar. So here we have small triangle inside of the larger triangle, ACT. They do have a shared angle, and that shared angle is angle C, which is in the small triangle and also in the big triangle at the same time. And since we do have parallel lines cut by a transversal, we do have these congruent corresponding angles. They're in the same spot where the parallel line hits the transversal, top right. So we do have the triangles are similar by AA. So now we're all set to pick which proportion is correct. So we have to make sure that when we are looking for the correct proportion, that we end up picking a proportion that uses sides from the triangles, because the triangles are what's similar. So it's got to be the corresponding sides from the triangles that are in the proportion. So in number one, we have CE, which is from the small triangle. We have CA, which is the corresponding side to CE from the big triangle. So far, so good. We just need to make sure that the other side is set up the same way. If this is small over big, this got to be small over big as well. CS is another side from small triangle, and it does correspond to CT from the large triangle. So this is correctly set of proportion. I do want to go through the other ones just to talk about why they're not correct. So in number two, CE is from the small triangle. ES is also from the small triangle. You can have small over small. On the other side, though, we need to have the side from the big triangle that corresponds to this one from the small triangle, and the side from big triangle that corresponds to this one from the small triangle. So corresponding to CE would be CA, but that's not what's here. What's here is EA. EA is not the full side of the big triangle. In fact, EA is not a side of either of the triangles. It is a side of this quadrilateral that is at the bottom. So that's not going to be okay. Goodbye to that answer. Moving on to number three. CE is from the small triangle. EA, same issue as this one over here. EA is not a side from either the small or the big triangle. It's not from either of the similar triangles. It's a side of this quadrilateral at the bottom. So when we're making a proportion, we need to make sure that we're using the sides from the similar triangles. So this is not good. And then finally, CE, once again, side from the small triangle over ST. And there's an issue again because ST is not a side of either of the triangles. It's not the side from the small triangle, that would be CS, and it's not the side from the big triangle, that would be CT. It's a side of this quadrilateral at the bottom, so that's not going to be okay. So answer choice number one is the correctly set up proportion. Moving on to number two. This one over here is supposed to have multiplication symbols in between. Oh, wait. It was supposed to be a proportion. So now we have the correct answer choice over here. Let's take a look at the question now that we have all four answer choices the way that they need to be. So we have two triangles, triangle XYZ and triangle SRZ, and they tell us in the diagram that XS and YR intersect at Z. That's not there for no reason. That's telling us we have intersecting lines. We have that letter X. So what we have are congruent vertical angles formed by the intersecting lines. And it also tells us that segments XY and RS are drawn perpendicular to YR. So XY is perpendicular to YR, so it makes a right angle with it. And RS is perpendicular to YR, so it makes a right angle with it. So already I'm seeing two congruent pairs of angles, the congruent right angles, the congruent vertical angles. I know the triangles are similar to each other. Don't get fooled by answer choice number 2. That does not say similar. That says congruent. I don't know these triangles are congruent. AA proves similarity. AA does not prove congruence. To prove triangles congruent, you would need a congruent side somewhere. And we don't have that. So goodbye to that answer choice. Oh, wait. So I can also say goodbye to answer choice number 3 because I don't know anything about the side lanes. So I won't be able to tell that XS is congruent to YR. So let me get rid of that. Goodbye to that one. So now this made it really easy. I'm talking about similar triangles here. So either it's going to be this proportion that's correct or this product that's correct. So let's check it out. First, let's check out the proportion. And let's see if it correctly puts corresponding parts together. Because the proportion is a little bit easier to check out than the product in terms of the corresponding parts. The product, we would have to first rewrite as a proportion. So let's check out 4, and let's hope that that's the answer. XY is aside from this triangle over here. I'll call that the triangle on the left since they both look about the same size. Usually I like to say small and big triangle, but they both look the same. SR, so that's the corresponding side to it from the triangle on the right. So since this is set up left over right, I need to make sure the other side is also set up left over right. So YZ is from the left, and RZ does correspond to it from the right. So answer choice 4 is the correctly set up proportion. Moving on to the next one. And if that wasn't the answer choice, you would have to first rewrite this as a proportion. Just make sure if you rewrite this as a proportion instead of a product, that it does cross multiply to give you this product, so that way you can check it out. But we didn't need to here because 4 was the correct answer. Okay, this one was a little bit difficult because you might not see what corresponds if you don't draw the triangles facing the same way. The two triangles, the big triangle and the small triangle inside of it, are not facing the same way, even though it might seem like they are. The question, it does tell us that angle C is congruent to angle OTU. So already, since those are congruent, they have to match up to each other. They have to correspond. Because when we have similar triangles, the corresponding angles are congruent. So if these are congruent, they have to correspond to each other. So that already tells me these triangles are not facing the same way because these are not in the same spots on the two different triangles. So I'm going to label this triangle with the givens, but then I'm going to redraw the triangles as well. PU is 4, OU is 5, and OC is 7, and we're finding the length of ST. Now I'm going to redraw the two triangles, and I'm just going to draw them facing the same way. I'm going to just leave the larger triangle facing the same way that it's at now. And then when I redraw the smaller triangle, I want to redraw it so that the angle that corresponds is in the same spot. And that angle was at angle T. Now, since small triangle was inside big triangle, they're going to have a shared angle. That shared angle is angle U between the two triangles. So I know that angle U has to correspond to itself because it's shared between the two triangles. So if I put angle U over here in the big triangle, I have to put it over here in the same spot in the small triangle since it's got to match up. And that leaves angle O, the last one in that triangle, to be up here. And now I can relabel because I know that OU is 5. I know that TU is 4. And I know that OC is 7. Unfortunately, OC is not a side of either of the triangles. It's a side of this weird-looking quadrilateral over here. But if I add the 7 and the 5 together, I can get CU, which is a side of the big triangle. And that's 12. And what I'm looking for is ST, but ST is not on either of these triangles. But SU is. So if instead I find SU, which is aside from the big triangle, then I can take the whole side, subtract 4, and get ST, which is what I'm looking for. Now I'm going to make a proportion. It doesn't matter. I'm going to just do big over corresponding side from small equals to big over corresponding side from small Doesn't matter. You could do small over big equals small over big, as long as you keep the corresponding parts together. Okay, so SU is what we just found, and that's 15. But that's not what we're looking for, so don't get tricked by number 4. We're looking for ST. So I'm going to subtract off 4, and that gives me 11. Moving over to number 5. In number 5, there is a lot of words, but it's actually a pretty straightforward question once you understand what the words are saying to you. So in the question, it does say that the streets are parallel to each other. So that's important because notice how we have small triangle inside of the bigger triangle. And since we have those parallel lines, we have the shared angle between them. Well, that's not due to the parallel lines, that's just a shared angle. But due to the parallel lines, we have the congruent corresponding angles. We know the triangles are similar by AA. I'm going to erase those markings so it's not confusing. But the point of having the parallel lines was so that you know the triangles are similar. The small triangle and the big triangle are similar to each other, so you know their corresponding parts are proportional. It says here, the distance between the intersection of Ridge Road and State Street. So the intersection of Ridge Road and State Street. State Street, Ridge Road, here is where they meet. That's their intersection. And where the railroad tracks cross State Street. Here's the railroad tracks. Here's State Street. Here's where they cross. And that is given as 12. What is the distance between the intersection of Ridge Road and Main Street? Here's Ridge Road. Here's Main Street. Here's where they intersect. And where the railroad tracks cross Main Street. Well, here's the railroad tracks. Here's Main Street. Here's where they meet. So this is what we're looking for, that distance. So since we know the triangles are similar, we can easily just set up a proportion. We know this side from small triangle is 5. The whole side is 5 plus 5, which is 10. So I can do 5 over 10, small over big, equals to small over corresponding side from big. And then I have 5x equals to 120. And I can divide by 5. Let me do that super quickly. And that is 24. Also for this one, once you identify how to label the diagram, you can see the scale factors too, because 5, 10. So the scale factors too. So once you labeled this correctly and you figured out that we're looking for this, 12 times 2 is 24, and done. Okay, moving on to the next one. So we're talking about two triangles. I don't see them. I'm going to draw a picture. And they're in a ratio of 1 to 2. So that means this is the 1 part of the ratio because it's written first, like this one. And this is the 2 part of the ratio because it's written second, like this one is. So this one, the sides are going to be double the sides of this one. So BO is x plus 3. GR is 3x minus 1. And we need to find the length of GR. So this is the one I'm looking for. So I can use the ratio to set up an equation because I know that to get the bigger side, I would have to double the smaller side because it's a 1 to 2 ratio. So to get from the smaller one to the bigger one, I would have to double it. So I can just distribute. And let me really quickly solve my equation. Subtract 2x, add 1. My bad. I was like, why is my answer coming out so big? This was x plus 3. I wrote x plus 30. Okay, so subtract 2x, add 1 to both sides. X is equal to 7. You got to plug in to find the length of side GR. 21 minus 1 is 20. There we have it. Okay, we have the next one over here. So we have triangle CED, and they give us some measurements over here, and they want us to explain why AB needs to be parallel to CD. Well, if the triangles were similar to each other, then I would know that. So if I could show the triangles are similar to each other, then I would easily be able to explain why AB is parallel to CD, because already the smaller triangle is inside of the bigger triangle. So already they're going to have this shared angle over here, angle E, because angle E is in the small triangle and the big triangle at the same time. Let me just use one marking on it so it doesn't look all messy there. And I already know two of the sides from small triangle, so this is looking like an SAS situation to me. But let me just see if the corresponding sides are in fact proportional. So this side, this full side from the big triangle would be 8.75 if you add the two parts together. And this full side would be 10.5. Let me try out the scale factors here. So I'm just going to do side from big triangle over corresponding side from small triangle. That's 8.75 divided by 3.75. And that is approximately 2.3. And then if we do 10.5 over 4.5, the other side from big triangle over the corresponding side from small triangle, that's the same thing. So the scale factors are the same. This is an SAS situation. So we have to fully explain why this is SAS and how this also proves that AB is parallel to CD, because that's actually the question here. The question is not to show that the triangles are similar. So let me get some space here and we will make an answer. I don't want to write this big. I want to write small. There we go. Okay. Since CE over EA was equal to DE over EB, and since angle E was congruent to angle E due to the reflexive property, remember it was the shared angle, triangle AEB is similar to triangle CED by SAS. Since they are similar, their corresponding angles, angle EAB, I'm just picking two, and angle C, and I'll put those in the diagram as well so you guys can see them. That is this one and this one. I just chose those. Are congruent when corresponding angles are congruent, lines cut by a transversal are parallel. Remember, corresponding angles are congruent when we have parallel lines, and they are also a way of proving we have parallel lines. Just like showing that we have congruent alternate interior angles proves lines parallel, showing that we have congruent corresponding angles proves lines parallel. So I'm going to just end here, making AB parallel to CD. And that's a complete response. It fully explains how I figured out that AB was parallel to CD with no jumps, no skips, nothing in between. Okay, moving on to this one over here. I'm just going to graph this real quick. Okay, so we are proving in this coordinate proof that small and big triangle are similar to each other. So already I'm going to say that angle E is congruent to angle E due to the reflexive property. And then I do need to use calculations to show that sides are proportional. And you could use SSS instead and show that all three pairs of corresponding sides are proportional. I'm just going to do SAS because for me it's a little bit easier. So what I'm going to do is I'm going to find the length of EF and the length of EH, and I'm going to find the length of EG and the length of EJ so I can see that they are in fact proportional. So I'm going to pause the video so that way I can use distance formula really quickly for EF, EH, EG, and EJ. So here I have my lengths of EF and EH, and you can also tell they correspond from the letters in the name. EF is the first two letters, EH is the first two letters, so you can definitely use the letters of the triangle names to match up corresponding parts if it's given to you. And I just divided them to find the scale factor, which was 2. And then I found EG and EJ, and I divided them once again to find the scale factor, which was 2. And I ended with a concluding statement, which you need in order to get full credit on a coordinate geometry proof. Since two pairs of corresponding sides are proportional and the angle in between is congruent, the triangles are similar by SAS. Okay, here we have a directed line segment. We need to divide it a 1:5 ratio. A 1:5 ratio is a fraction of 1 over 6 because there's a total of 6 parts. 1 plus 5 is 6, and that gives you the denominator. For the numerator, you always use the number on the left. It doesn't matter, you always use the number on the left. So let's use our steps. So I'm going to find the x coordinates and the y coordinates, and it's the same 3 steps for each one. First, we're going to find the change in x and the change in y. So I'm going to put that here, the change. This is not written out nicely. The change in x and the change in y. So for the change in x, I'm going to do ending minus starting. So that's 6 minus -6, which is 12. And for the y coordinates, I'm going to do the same thing. I'm going to do ending minus starting, y2 minus y1. And that's 9. Now what we're going to do is we are going to take our result from the first step and we're going to multiply by the fraction that we created from the ratio. So that would be 1 over 6 here. I'm going to take the result 12 and I'm going to multiply by 1 over 6 and that's going to give me 2. I'm going to take the result here, which was 9. And I'm going to multiply by 1 over 6 and that's going to give me 9 over 6, which simplifies to 3 over 2 for 1.5 if you're using the calculator. Okay, and then finally, I'm going to add the start coordinate. So that means from your starting point to this 2, I'm going to add the starting x coordinate because I'm working with the x coordinates here, and that would be -4. And to here, my result, my 3 over 2, or my 1.5, if you wrote it down as 1.5, I'm going to add my starting y coordinate from my start point because I'm working with the y coordinate here. And 1.5, which is 3 over 2, plus -2 is -1/2 or -0.5. So the x and y coordinate of the point that divides line segment xy in a 1:5 ratio is the point -4, -1/2. Also, I forgot to mention, this question is always on every single Regents exam. So if you know your 3 steps, that's a guaranteed question that you can get right. Easy points to get. You just got to know your 3 steps. Okay, here we have a situation where we have a big right triangle, and inside the big right triangle, we have altitude that's creating 2 smaller right triangles. So I'm thinking right triangle altitude theorem because I see this setup. I'm thinking Hills or SAS. They tell us that the ratio of SQ to QR is 1:4. So I'm going to represent SQ, which is the one part of the ratio because it's written first, as 1x, or just x for short. I'll put the 1x here so it's easier to see. And I'm going to represent QR, which is the 4 part of the ratio, as 4x. So we have the 1x part and the 4x part. And anytime you have a ratio, you can represent segments in this way. Just put an x next to them because they're unknown, but they're in a 1:4 ratio. So this says that whatever this is 4 times that. And what we need to find is the total length of SR. So I'm going to put that as a question mark. So I'm going to ask myself, Hills or SAS? Do I know anything about the altitude? Yes, I do. I know that the altitude's 8. SAS, altitude rule. So let me write down my SAS over here. And the two segments of the hypotenuse are 1x and 4x, or just x for short. And the altitude is 8. 4x squared is equal to 64. Let's take our 64 and let's divide by 4, and that is 16. And then if we take the square root, x is equal to 4. So that's not our answer. That means SQ is 4, and that means QR is 4 times 4, which is 16. So we do need to add them together to get the whole segment SR, which would then be 20. Moving along over here to this one, it has like a complicated word problem, but if you look at the diagram, I see big right triangle. Look at that right angle there, with an altitude that's creating two smaller right triangles. If this is 90, then this has to be 90 here as well. So we have a right triangle altitude theorem here once again. Remember, I told you the diagram's always going to look the same when you have to use Hills or SAS. So here I'm going to ask myself, am I using Hills or SAS? So that depends on what the question's asking me. And there are two parts to this question here. The first part is saying, determine and state the distance between the park ranger station and the lifeguard chair. P for park ranger station, L for lifeguard chair. I like when they label it by what it represents. I don't have to fully read the question. So that's what we're finding first. So that's on the altitude. So since I have information about the altitude, I'm going to use SAS here. Or at least I'm going to try to use SAS here. But the problem is, when I go to try to use SAS, I realize I need both segments of the hypotenuse. But I only have one. I only have this 0.25. I don't know what FL is. So I'm going to have two unknowns. I'm going to have the altitude, which I'm looking for, which is unknown. And I'm going to have FL as an unknown. So that tells me maybe I can't directly use the altitude rule, even though I'm interested in the altitude. Well, maybe I'm going to use the leg rule because I do have information about a leg. And maybe I can then get the information I need to find the altitude. Maybe I can then get FL, which I need to find the altitude. So what we can do here is we can represent, instead of representing the altitude as x, we can represent the hypotenuse of the big right triangle as x. And the segment would be the part of the hypotenuse directly below the leg. And from here, we can cross multiply. And we can see 0.55 times 0.55, and that is 0.3025. And then if I divide 0.3025 by 0.25 to get x by itself, x is 1.21. That worked out nicely to the nearest 100 decimal places. So that tells me the whole hypotenuse here is 1.21. So what I can do now is I can do 1.21 minus the part I already have, which is 0.25. And that gives me 0.96 over here for the other segment of the hypotenuse. And now I can use SAS. I'm just going to call the altitude y because I already used x to represent the hypotenuse before. And now, since I know both segments of the hypotenuse, I'm able to now set up my altitude rule, and I can solve for the altitude. So that is 0.96 times 0.25, and I got 0.24 is equal to y squared. So now I have to do radical 0.24, and it does say it's round to 2 decimal places. So y is approximately 0.49. So the altitude is approximately 0.49. So you might have said, oh, wait, this was a right triangle. I didn't have to do all that. And you're absolutely right. You could have used the Pythagorean theorem. You could have done 0.25 squared plus b squared is equal to 0.55 squared, and you would have gotten the exact same thing. I just wanted to show it to you guys with Hills and Sess. And also, it kind of killed two birds with one stone doing it in this way, because the next part of the question is asking about the distance from the first aid station to the campground, which I already have now. I already know that's 1.21 because I found the hypotenuse of the big right triangle when I set up my leg rule at the beginning. So you could very well have done it with Pythagorean theorem, but you would still have to do a little bit more in order to get this 1.21 that we had in order to answer the second part of the question. Now I see that Gerald is not right. This is less than 1.5. Gerald's wrong. So I'm going to put here, Gerald is not correct. Distance is 1.21, which is less than 1.5. So although there was an easier way to find the altitude, I like the way I did it because that way I found everything I needed for the next part of the question, and I practiced using Hills and Sess. Okay, now we have a proof over here. So I'm going to work backwards because I do want to show you guys that even if you get stuck and you don't know how to answer the proof, there's lots of points that you can get. You don't have to leave the proof blank, which unfortunately a lot of people do. So I'm going to start off working backwards with the proof statement. So that's EH times CH is equal to FH times AH. Now remember, when we get a product like this, that means multiplication, product comes from a proportion. And when we have a proportion, we cross multiply it to get a product. So remember, we have a fancy justification for cross multiplication. And what it says is in a proportion, the product of the means equals the product of the extremes. It's just a fancy way of saying cross multiplication. Yes, you do have to use this reason. No, on the Regents exam, they will not give you credit for writing cross multiplication, so I will not either. Now, this reason mentions a proportion. So to get this product, we first need to have a proportion. So what we're going to do is we're going to take the four segments here, and we're going to order them into a proportion, and we're just going to double check that the proportion we make cross multiplies to give us the product that we're proving. So I'm just going to put in EH, AH, CH, FH, and let's just double check. EH times FH. Oh, that's not right. Let me reorder them. I need EH times CH. So let's check that out. EH times CH, good. FH times AH, good. So double check your proportion, easy points to get. Okay, now we know proportions come from similar triangles because similar triangles have proportional corresponding sides. So before we can prove this proportion, we first need to have similar triangles, like the reason says. But I don't know which triangles we're focusing on because there's two small ones, and there's also larger triangles in this diagram as well. So that's when we're going to look at our proof statement. EH, CH, FH, and AH. So I see that the segments in my proof statement are coming from the smaller triangles. So I know my goal is going to be to prove triangle AEH similar to triangle CFH. And I know since this is a two-column proof with no numbers, it's going to be through AA. Now, I already have half the proof done. And I didn't even look at anything that was provided to me in the givens. I already have half the proof finished. So you don't have to get 0 points, even if you don't know how to get the angles to prove the triangle similar. Now I'm going to take a look at the givens. I'm not going to write all the givens down just because I don't want this video to take all day and to run out of space. But EF is parallel to AD. EF is parallel to BC. And AD is congruent to BC. That is given. So EF, where is that? right here is parallel to AD. And then it tells us that EF is also parallel to BC. So I'm going to stop right there. If this is parallel to this, and this is parallel to this, well, that means that this has to be parallel to this. I'm going to put that here. AD is parallel to BC. And we call that the transitive property of parallelism. You do have to be specific and say that that's the transitive property of parallelism, because transitive property is normally about things being congruent. If this is congruent to this and this is congruent to this, then these have to be congruent. So since we're talking about parallel and not congruence, we need to specify that in our reason. This is parallel to this. This is also parallel to this. So these must be parallel to each other because they're both parallel to the same third segment over here. Transitive property of parallelism. And our last given was that these are congruent to each other. And look, now I have a parallelogram. So I know, and I'm going to put that over here, that quadrilateral BADC is a parallelogram. And I'm just going to abbreviate here. It has one pair of opposite sides that are both congruent and parallel. The full reason would be if a quadrilateral has one pair of opposite sides that they're both congruent and parallel, it is a parallelogram. Okay, now from knowing that, I can say that AB and DC are parallel. And that's because opposite sides of a parallelogram are parallel. And that was important because now if you take a look at your letter Z, you can say that the alternate interior angles are congruent. So I'm going to put that here. Angle EAH and angle HCF are congruent. Sorry for this messy congruent symbol. I'm going to abbreviate because I'm running out of space. Alternate interior angles are congruent when parallel lines are cut by a transversal. Sorry for the abbreviations here. And then finally, we also have our congruent vertical angles. I'm going to put that over here. Angle AHE is congruent to angle FHC. Intersecting lines form congruent vertical angles. So remember to work backwards. Product last. Proportion is where the product comes from. Before that, we proved the triangle similar. Always by AA and the two-column proof. Look out for your congruent angles. Generally, always alternate interior angles or vertical angles. If it's not both of those, it will most likely be one of them. So be on the lookout for those kinds of angles. Okay. One more question over here. And just like the last one, we are proving a product. So I am going to work backwards, just like I did in the last one. And I should go back and number my steps at the end. So that's 7, 8, and 9. Here we go. Okay, so I'm going to start from the end. I don't know how much space I'm going to need, so let me go like all the way down over here. So our proof statement is AF times EF is equal to DF times BF. We know it's going to be the same reason anytime we're proving a product. In a proportion, the product of the means equals the product of the extremes. Before that, we know that we need a proportion. So let me order the proportion. AF, DF, EF, BF. I just randomly placed those. Let's see if it cross multiplies to give me what I need. Oh no, AF times DF. That's not right. I need AF times EF. So let's edit. I'm going to swap EF and DF. And let's see if that's good. AF times EF, DF times BF. All good. And that's because similar triangles have proportional corresponding sides. So before the proportion, I have to prove the triangle similar. There's only two triangles in this diagram. There's only triangle BAF and triangle DEF. But if there were more triangles, make sure to use the proof statement to help you out. AF is over here, EF is over here, DF is over here, so that's one, and BF is over here, that's another one. So the proof statement can help you identify which triangles you're working with. It's going to be for AA since it's a two-column proof and you have no numbers. Once again, half the proof is done, and we haven't even looked at the question. Now let's look at the givens. We have parallelogram ABCD. So I know a lot of stuff about ABCD because I know it's a parallelogram. So I got to think about what's going to help me get AA. First, I see my vertical angles. Remember, always look out for your vertical angles. Vertical angles are usually always part of the similar triangles questions. And let's look out for alternate interior angles. I do see a letter Z. But remember, in order for the alternate interior angles to be congruent to each other, we do have to first know that the lines are parallel. And wait, we do because we have a parallelogram. Perfect. Let's put this in. EA is parallel to CD. And you don't need to say that since CD is parallel to BA, that CE is also parallel to BA. You could say parts of parallel lines are also parallel. You don't have to say that, though. Nobody's really going to get on you for that. It's not necessary. We don't need to be that complete and thorough. So I'm going to put that here. Opposite sides of a parallelogram are parallel. And then once we know that, we can say that angle ABF is congruent to angle DEF because alternate interior angles are congruent when parallel lines are cut by a transversal. Sorry for the extremely messy handwriting. And then all we needed was our vertical angles, which is angle BFA and angle DFE. And our reason for that, intersecting lines form congruent vertical angles. And that's it.